So practice 10, we'll look at continuing to use convolutional neural networks, CNNs, but this time on the CIFAR10 database or data set. This is a data set of images that we'll look at, and we'll see some examples soon. And so we've got a practice notebook here that you can open up and get started with. One warning is that training that network is going to take often hours, like 4 hours or more sometimes. So you should plan to be able to do this multiple times, and at times where you can run it and then come back later, hours later, and see how it's doing. And so we'll talk about that, and we'll want you to run it at least 3 different times here. So keep that in mind. Okay, so let's go into the basic CIFAR database set. So the data set is just small 32 by 32 images, and CIFAR10 has 10 categories, so dogs and cats, horses and trucks and planes and automobiles and birds. So these are the images, and the idea is that the computer should be able to recognize an image, so given an image to tell if that's a dog or a frog or a horse, that sort of stuff. There's also a version called the CIFAR1000 data set. But this is, that has, or I mean, the CIFAR 100, and it's 100 different labels here. So this is just a subset. So there are generally 60,000 images in here, each 32 by 32 pixels in 10 classes. We'll be working with the 50,000 training images. And of that, we're going to actually break it down into some training tests. And then there's 10,000 images that are used to actually evaluate the model that you don't test on at all. And so we'll be using those somewhat. We'll actually be using the Kaggle challenge here. And there's a spot in Kaggle for these that has this data set in it. And we'll talk about that. They actually have a bunch more testing images than the 10,000. We'll talk about that later on. Okay, so normal stuff, you have to set up your libraries here. And then we're going to read the images. So this is going to read the whole set of images from GitHub and copy it to your computer. So when you run this on your computer, it should show up in your files area and have it over there. So let me just connect up and do that. Now, one thing when you're connected, some of this is going to be a little bit slower, so you might want to check your runtime. If I bring up the menus here, you can change the runtime type to a GPU here rather than a normal thing. There's also something called a TPU. GPU will speed things up with this sort of image processing, so you might want to change that. So again, if you're in Colab, you can go into runtime and change the runtime type. If you're on your own computer, if you have a particular type of GPU, you can set up this to run there, but it's probably may not be worth the effort for just a couple exercises here to set up the GPU environment, because it takes a little time. But if you're interested in that, contact me separately and I can give you some suggestions on how you do that. We've set up a couple machines that way. So again, we're going to clone this, all the images, the 50,000 images from GitHub here. And we'll talk in a little bit why we're cloning it from GitHub rather than Keras or some other site. This is also built in. This is a real common data set. It's actually built into a lot of systems. So Keras has its own built-in version of this. But again, we're going to avoid that for a couple reasons that we'll talk to later. So we're cloning it from GitHub here. So when we do that, under your Files tab here, you should see, let me refresh this, the CIS3115 training data, and in that there'll be train images by category and validate images by category, and then there'll be folders for each of the types underneath that, and we'll talk more about that. But that should be, if you hit refresh and after you've cloned, you should see that. So one of the things you have to look at is setting up some convolutional neural networks for this. Again, we can review. I left a review in here for the different types of layers here. This is a nice little article on some different ways or a possible way of setting up a CNN for that, and we'll continue to look at other ones in a sec. So here's just a basic neural network. Again, our input shape is 32 by 32 pixels. These are color images, so the depth is 3, red, green, blue, RGB. And so we finish or feeding that input into our convolutional neural network, 8 filters, each 3 by 3, and we're going into another convolutional neural network or layer, 8 filters, 3 by 3. Then we're pooling them together, 2 by 2, so this will shrink the size of the network in. We're doing another convolutional neural network, this time with 16 filters. We're flattening it and doing a dense unit of 32 filters, and we're outputting it. Our output size is 10 because there are 10 categories, and we're doing our softmax here. So this is a relatively small neural network for this sort of stuff, and it will not perform that well compared to some larger ones. This is the type of challenge where we're now getting into deep neural networks will actually perform better here. So adding more layers to that, and that's why this, you might want to look at this article here is a good starting point. But there's actually, if you look at CIFAR on the internet and convolutional neural networks, there's lots of resource for people suggesting ways to do it. The way this is set up now, we're doing a neural network summary after we set up the neural network, and this just shows this sample configuration. So again, our different layers here we've set up, and this shows the size of them. So we start out 32 by 32 images, but we lose 2 pixels, 1 pixel on the left and the right, as we apply these filters. So we end up with 30 by 30, then 28 by 28. Then we max pull it down to 14 by 14. We filter it again, 12 by 12. So there's ways to avoid this, but right now we're losing 2 pixels for every time we apply convolutional neural network. So if you want to set up your network here so that it doesn't shrink each time, you've got to look in convolutional neural networks. One of the parameters is, besides the kernel size and filters, is the padding. You can set the padding equal to same here, and it won't shrink the size. Let me show you that. So now I've added this padding equals same in here. And so then our neural network it keeps at 32 by 32 until we do a max pooling, and then it shrinks to 16 by 16 here. And we could do more layers here. So if you have padding here, it will add padding around the image so that you can apply the convolution filters all from one edge all the way to the other edge. Okay, once you get that started, again, we've got our early stopping if we want. We can also reduce the learning rate if need be, so you feel free to play with these if you want. I've got some general parameters set up here if you want to just leave them alone. Now let's talk about reading our images. So in Colab, our images store out here. Now, if you're working on Jupyter Notebooks, when you download this, you'll have to download 2 things from GitHub, and I'll post those both to the here. I've only posted one, but there's the training data you also have to download from GitHub, so I'll add that here. And so you may have to change this folder to point to the right folder on your local machine. Let me know if you have some questions on how to set that up. But we're going to set up a training and a validation folder, again, because we're going to look at 2 sets of files. We want a train images by category and validate images by category in here. So those are both set up here, and then we'll read. This is just the directory where we're reading those from. In Colab, /content is the default kind of root folder, and then everything else is underneath that. Now we're going to use these image generators, which are part of Keras, which is done for most advanced image processing. And we didn't use them last time when we were just starting with convolutional neural networks. But most powerful convolutional neural networks use these. Image generators allow you to read images in and do some adjustments for them, particularly if you don't have that much training data, to adjust the training data There's a couple articles. This is a good one from the Keras blog, talks about classifying images with very few input images. And this is another article that has some good visualization of some of the more advanced image augmentations available for this. But what we do is we specify image generators, and we specify some different things for them. So let's say we're reading in cat images and we want to be able to shift the images a little bit to the left or right each time, so that if you have a cat there, it'll be maybe shifted a little 1 or 2 pixels left or right or up or down. We could have shift, width shift or height shift, and this is a percentage. So 10%, 0.1 is 10%. So if our images are 32 by 32, that would give us a shift of up to 3 pixels here. Similarly, we can do what is called a shear, or we can zoom in or out of images. Here you can also rotate an image, and this is most of these are percent of the image. This is a number of degrees, so if 360 degrees is all the way around, maybe 10 degrees or less. You don't want to do too many shifts to this, because this can distort the image. So initially I'm going to start without very many augmentations. So we're always going to rescale our images. So our pixels are always between, our RGB pixels are always between 0 and 255. So we're always going to rescale every pixel by dividing it by 255. So now it's between 0 and 1, because neural networks perform better in that range. The one other thing I'm going to add is add a horizontal flip. So this will flip this. Some of the images will be flipped horizontally, so the cat might be left side or right side. Now there's also a vertical flip, but I'm not going to include that because, again, cars are usually not upside down and things like that. So I'm just going to try the horizontal flip to start and our scale. Now that's when we're training our data. When we're testing our data, we don't generally want any of this except for our rescaling. So I have a special generator here just for when we test our images out. And so then all we're doing is rescaling the images. Again, if there are some other things you want to look at, certain brightening or certain features that you want that should improve it, you might want to consider, ask yourself, is that something that should be also applied to the test images here? Okay, so we are then going to, once we have that set up, we're going to read these images from a directory. Now, the normal CIFAR data is all the images are basically in one folder or all in memory at one time here. But when we're working with bigger data sets, particularly like with the upcoming project, we can't load in all the images into memory, and so we often use this flow from directory idea. And so once we up here, let's see, we define our training data generator. It's an image generator, so that's what we call it, train, and we also have a test one, but train data generator is defined here. And then we can use that train data generator and we say flow from directory, and we can specify a folder. And this is the folder we created up here, our training folder. And this is where it's at. Our training folder is here. So it will go look out in that folder for images. So that's what this train generator will do. It will use that image or augmentation settings and go out and look at this folder. And so again, if I look out in that folder, train images by category, there's a subfolder for each of the categories. And then inside this, there's a whole bunch of cat pictures, a whole bunch of deer pictures, a whole bunch of airplane pictures. Now originally the CIFAR data does not come that way, so I've actually had to copy all those images into those folders, and so I use this short code that copies all the data by their index. So we're given a spreadsheet that lists each image name and what label it is, and then with that we go through and copy the folders to the right spots. So that's actually been done for you here, and that's why we're reading these images from GitHub rather than like the default Kaggle images. And again, for larger image challenges and larger, it's just much more common out there that this is how it's often done. Though the small CIFAR data set is often not set up this way. So, but I've reformatted it this way so we can use it that way. Okay, so we're going to use this flow from directory. Here's our folder. Um, Here's our image size. We're not going to resize it. Sometimes you can actually resize your images here, but we're not going to resize our images at all. And we're going to specify a normal batch size of 32, and this is the default batch size, and that's not that important. We generally want that as large as possible within the memory constraints. So if you are running out of, if you're working with a larger network and you're crashing because of memory, or you see your RAM getting way up here, you can drop the batch size down to 16 or 8 if needed. Okay, so when we do this, we read it in and it finds 45,000 images in 10 classes, and then a separate, our validation stuff, I've separated out 5,000 images for validation purposes for this. So now we're going to train our network. Go down here and train this. So we've defined a neural network above. We call it NN, and we're going to say fit generator. And we're going to use this train generator. This is the generator that was defined right here. And also notice the validation generator was defined right there also. So this is the one that's defined to flow from the directory and set that up. So we say fit with this train generator. And we also say we're going to use the validation generator, validate stuff. Now, it's going to randomly pick up images from these directories. So it doesn't just go through all the images, it's randomly picking images. And so you just say, how many images do you want to do? So each epoch, we're going to say, is going to do 200 images. And again, we can increase this. This could be up to easily 1,000 if you want. And how many epochs do you want to do? And we're going to do 50 epochs. And again, this you probably want to do this more. So originally, like if you're doing, there's 50,000 images, and if we're doing 200 epochs with 50 images each, that's only getting a total for all the training of 10,000 images, and we have 50,000 images. So we're only seeing a fifth of the images, and we're rarely seeing any images twice here. But watch, this will take a long time. Even with the GPU, I was running 1,000 images through this, and it was taking a couple minutes. And so it could take up to 4 hours to do 100 epochs with 1,000 images in each. And that would give you, again, 100,000 images. So that would go through all the images basically twice about, which would probably be a better choice. But initially, we'll just start here. Now, let me just run this so we can see how this runs. Oops, I forgot. I've got to actually run this code up above here. Let's see, where did I end up? So I did this. Okay, so then it should run the training here. And again, we're doing 200 epochs. So the steps per epoch is the number of images processed per epoch, and the epochs are how often, again, we adjust the training rate and stuff like this. So again, we're only doing 200 images, so it should go relatively fast here. So this is taking, 24, about 30 seconds, half a minute for each of these to run through. But again, we're only getting to 10,000 of the 50,000 images here. One thing we'll want to watch then is your accuracy. You should be able to get this accuracy up 60-70%. Top performers get up to 90%. So that's certainly something we can shoot for here. Now, once you're done training, you can plot this training stuff. This is the type of curve you'll generally see. The accuracy should start low, around 20%, and creep up, 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 up. So again, we're getting up above 60% this time when I ran it last, but I'm not up to the 70 or 80%, but 60% is a good range, so you can kind of watch that. But I'm also seeing it starting to plateau. It's not learning so much, and the loss is getting down there, so I'm not seeing much loss, but I'm still seeing loss above 1, so there's still some learning going on. So maybe running this longer would help for this. I'm not seeing much overfitting. My testing and training are about the same. If my training were going up to near 100% and my testing were still down here, I would worry about that, and I might want to introduce some dropout or some other noise in here. But right now I'm seeing these two lines very much in sync, meaning that I'm not memorizing the data. And again, because I haven't seen all the data, that certainly makes sense for this. Okay, so you want to do your training a bunch of times, and again, this will take a while. Now you may this is probably where you'll leave your machine running. There's some information about timeouts here. So let's see, where is this? So generally, if you the timeout on this is 90 minutes if you close the browser, but if you keep you can run this for 12 hours if you keep your browser window open. So what you should do is keep this window open and this cell running. I would actually run this cell afterwards so that you get this plot afterwards. I actually would run the whole notebook. You just go up here and say run all possibly and run the whole thing. But it will, it will get this one cell is going to take a long time to run, hours. So just wait for that. And again, you might want to adjust your laptop or your power supply. If you just go down and look under search for power, make sure your machine isn't going to sleep or shutting down after an hour of inactivity. You should probably keep it plugged in and hopefully running for a long time. Try to keep this browser window open for a couple hours and come back and see how it is. And again, I believe it'll stay active for 12 hours if you keep this browser window open and your machine doesn't go to sleep or power down automatically. Okay, so try that, see how that goes. Now we want to see your final results here, and so we want you to post those results to the assignment. So we want you to post the results here. There will be a special Unit 10 progress report area where you can post your results here. And again, we'll use this certain format. Let's see, let's create a thread and it should show us the format. So we'll use this format where we want to say the title should be like CIFAR10, and then the accuracy that you've achieved, and then the layout of your network, how much you're training it for, and your results for that you can paste in there. So you can copy and paste a lot of that into this. And what we want to do is have all the students working on this, posting the results, sharing their ideas, and trying to improve each other's work for this. So. Okay, so that's the main thing. Now you can also submit this to Kaggle if you want. Again, we're doing this Kaggle challenge here. There are some issues. The Kaggle, to prevent cheating, there are only 10,000 images, and so sometimes people cheat on those. So what Kaggle has done is hidden those 10,000 images in 200,000 images, and so their testing set is 200,000 images with the 10,000 ones kind of hidden within that. And so this clone is going to take a little while, and yeah, I'm still working on getting this to work. Right now, if I copy that many images over from GitHub, it's not working. So I think I'm going to be copying over a zip file and unzipping it here. That's what worked most recently. So I'll finish that up. So at this moment, this doesn't work, but I'll post an update here to get the Kaggle results working, hopefully early this week. So that's your whole goal. Your job is to run at least 3 different tests for this. Now, I'm going to post one more requirement here, hopefully, and that is some links to some other networks you might want to try, some pre-built network configurations that you might be interested in trying. So I'll add a link for it. So if later on in the week, if you're looking for some better improvements, I'll post either to the discussion area or to Blackboard with some hints on some more complicated networks you might be willing to try. Okay, good luck.